University of Hamburg, Germany in 1999. And after that, she joined the wood technology at Johannem Research, Johannesburg, Australia, and applied R&D consultancy there. And after that, 2002 to 2005, Graz University of Technology, Australia, and she worked as delegate science officers to the Australia. They have done a lot of works on consultancy, timbers, engineering, wood technologies. And she also, since 2005, she is also the professor for product and productions in the timber engineering at Ostwestfalen-Lippe University of Applied Science and Arts, Lemgo, Germany, Department for Production Engineering and Wood Science, Wood Technology. And she is teaching the, what you call that, the different courses. And she's presently the head of the laboratory for timber engineering products and production since 2014. And she have done a lot of R&D projects on properties and utilization of palm woods. And we have opportunity, I meet her in Malaysia. We have a memorable photo with her. So please take the charge of this session. Now the session hand over to you. Thank you.
Thank you very much for the kind introduction. Yes, this was the last personal meeting before the lockdown 1.5 years ago, and I hope we will meet again in the near future. Thank you very much.
Inshallah, we can meet again.
I'm very happy to be chair to the moderation of session A2 about the wood, or the wood of oil palm trunks. And I would like to start, because we are a bit late, I would like to start with the presentation of Lena Heister. Lena Heister, she's PhD student at our university, so Ostwestfalen-Lippe University of Applied Sciences. She did her graduation, bachelor and master graduation at our university as well, and she worked even in her bachelor and master thesis with oil palm wood, so she has some years experience now with oil palm wood, and she will focus today on the glue laminated timber from oil palm wood, the build up, the production, and the elastomechanical properties. So Lena, it's up to you. And I think we have an MP4 because we have some technical problems. So there should be an MP4, so they recorded.
Lena, please unmute yourself.
No, if possible, you have a recorded MP4.
I think we did not ID 21. I don't think that we received that. Just a moment. I have a ID 23 and ID 17. I think I just check it that.
Yeah, again. But we get the okay that
as
you
per
receive
my
ID
folder
21 as well.
Midani of Shep, I can check again 7558.
Yeah. Sorry for the.
Have she sent to us that?
Yeah, she has sent to us, and Mohammed Midani answered 3 hours ago that he got it.
Okay, just a moment, I can check that, you know.
Yeah. Lena, is there a possibility that you do it here? We can try it if there is enough. If that. So. Professor Javad, you
I can.
Was looking. So in the meantime, I can report that Lena did her bachelor thesis on the elastomechanical properties. So she has a lot of experience with compression tests and tensile tests with small clear wood specimens. And in her master thesis, she started to grade lumber, oil palm lumber, and produced the first glue laminate beams. Within the project, within a bigger project we have together with our colleagues from the biotechnology. Professor Javad, do you have the presentation? Otherwise, Lena, can you share your screen?
Yes, I try.
So we try to do it if there's technical possibilities. So sorry, we have
Before the presentation.
pardon?
The MP4, the video, or
No, the original, because
okay.
the MP4 it won't work from your computer.
I hope that's working now.
This looks good. So if you have a full screen.
Is it okay? Can you see everything?
Perfect. Yeah, we see everything. Okay. So thank you very much, and sorry. Perhaps you can do the presentation now.
Yeah, okay. Hello everyone, and thank you, Katja, for your kind introduction. My name is Lena Heister, and I'm working at Ostwestfalen-Lippe University of Applied Sciences and Arts as a research assistant under the supervision of Katja. I'm delighted to be here today to talk to you about the topic of my presentation, root laminated timber from oil palm timber, build-up, production, and elastomechanical properties. My presentation is divided into 7 parts, and firstly, I will start with a short introduction and the aim of this investigation. Then I will look at the grading and the buildup of the GLT beams. Further on, I will talk about the material and the production. Afterwards, I will talk about the testing methodology and the results of the tests. And finally, I will summarize the content of the investigation in a short conclusion. So let's start with the introduction. The results of many investigations on the elastomechanical properties, for example, compression, tension, and bending of small test specimens of oil palm wood, show a high variation of the elastomechanical properties. As Katja already taught in a presentation on the properties of oil palm wood, there's a dependence between the density and the elastomechanical properties. When considering studies of large-scale test specimens for load-bearing products, there are only a few studies. This variation in properties can be directly attributed to the density distribution along the trunk cross-section, as you can see in the picture, and over the truncate of monolecudent plants to which oil palm belongs. Characteristic material properties are required for further industrial processing of oil palm timber into large-scale load-bearing products such as CLT or GLT. Due to the density variation within the trunk and the correlation between the elastomechanical properties and density of small test specimens, the density is the reason why grading is required. Now we come to the aim of this investigation. The basic idea of grading according to the density is to cut the valley into strips so that strips with a homogeneous density along the cross-section are obtained. The width of the strips is individual and depends on the density profile of the board cross-section. Then strips of comparable densities are edge glued together to achieve a raw material for the production of GLT. Only by this procedure, homogeneous bending values and an optimization of properties compared to the conventional way of how GLT lamellas are produced when made of oil palm timber can be reached. So, as my colleague Katja will give later more information on a presentation about grading of oil palm timber, I would like to give you now a short overview. There are no grading standards for oil palm timber. Softwood is classified into strength classes called C classes, and based on the strengths, mechanical or visual techniques can be used to determine strength by measuring the density of knots, for example. Due to the correlation between bending strength and density of small test specimens of oil palm wood, the calculation of grading limits for oil palm timber was made according to the standard for softwood. Therefore, the statistical correlation model was used to calculate the forecast limits. In this picture, you can see on the left side the density profile along the width of an oil palm board from the outer zone measured with X-ray. The density of the board varies across the width from nearly 800 kilograms per cubic meter on the left to approximately a density of 350 in the middle and up to 450 kilograms per cubic on the right side. When cutting full-size lamellas for the production of GLT as conventional, there will be lamellas with an inhomogeneous density distribution along the cross-section. The cutting of the lamellas is done alternating from the edges due to the tapering of the trunk. In comparison to the conventional way of lamella production, you can see on the right the same density profile and the procedure of cutting strips as the function of the density gradient across the board cross-section. The calculated density limits to achieve a certain strength are shown here as gray horizontal lines. The cutting limits are located at the intersection between the smooth density profile and the density limit value. In contrast to the conventional method, strips with individual width and homogeneous density distribution across the cross-section are obtained. For further processing of GLT lamellas, strips with comparable densities are edge-glued together to edge-glued timber. The lamellas are then cut off the edge-glued timber as in the conventional method. For the production of the GLT beams, the 30-year-old oil palm trunks from Malaysia were used. For the whipped lamella and non-whipped lamella-based beams, the same amount of boards was used. The arrangement of the lamellas in the beam design was selected in accordance to the moment effect in the beam during a bending load. That means that lamellas with the lowest density were arranged in the middle. The lamellas with the highest density were arranged in the lower lamellas and with the second highest density in the upper lamellas, as you can see in the picture. The density limit values results from the calculation of the grading to reach a strength class C10 and C14 calculated for oil palm timber. GLT beams of both strength classes and lamella structures were produced. Now you can see some pictures of the production. On the left side, there shows the cutting of the strips according to the density profile. And the middle piece is left over due to the tapering of the trunk. The picture in the middle and on the right shows the process of edge gluing density comparable strips with individual widths together. For pressing the beams, a timber press X for Mender Industrieanlagen in Minden was used. The dimensions of the press are 3.40 m in length and 1.20 m in width. The press has two pressing plates, which can be controlled separately by a hydraulic pressure system. These types of presses are commonly used for the production of GLT or CLT. The beams were tested in a standard 4-point bending test. Besides the determination of the strength, the local and global stiffness values were determined. The beams of strength class C10 were tested with a 20 kN testing machine, where for the beams of strength class C14, a 100 kN testing machine was used. Now we come to the results of this investigation. The table shows the values for the density, in addition the characteristic density values. The characteristic values were calculated in accordance with the standard, after calculation of the reduction factor Ks. In addition, and because of the small number of specimens, the value of the 5% quartile for a standard normal distribution was used for the reduction factor to calculate the characteristic value. This way of calculation was used for all characteristic values. The mean density of the whipped lamella-based beams is higher compared to the non-whipped lamella-based beams. All beams show a comparably high coefficient of variation. This diagram shows the relationship between the bending strength and mean density of GLT beams made of oil palm timber. For all beams, a positive trend between strength and density can be seen. The strength values of the whipped lamella-based beams are higher compared to the non-whipped lamella-based beams. The strength values of all beams, with the exception of the values of the non-whipped lamella-based beams of strength class C10, are above the targeted characteristic strength values. The values of the local MOE of all beams are shown in the single chart, in this single value chart. The values show a high scattering. Comparably high stiffness values of almost 4,000 and 5,000 newtons per square millimeter are achieved with different strength classes and beam setups. This diagram shows a positive trend between bending strength and stiffness for all GLT beams. The correlation between strength and stiffness is higher for whipped lamella-based beams compared to the non-whipped lamella-based beams. There's a high range of strength values at an MOE of 5,000 Newton per square millimeters. Now we come to the comparison of the global and local stiffness values. The diagram shows the standardized linear relationship between the local and global stiffness for softwood. In addition, the values for GLT made of oil palm timber are added. As you can see, the relationship for softwood does not apply for GLT beams made of oil palm timber. The consideration of the failure patterns. The most of the beams has failed in compression. The failure was mostly detected in front or behind the supporting timber and beneath the load introduction area, when the maximum longitudinal compressive strength was exceeded. After the compression failure, the beam continued to fail on the outermost lamella, loaded as tension, and below the compressive failure. To avoid buckling of the vascular bundles, some beams were tested under upside down loading of the lamellas. This means that the lamellas with the higher density are on top. The result shows different fracture patterns. A total of 5 beams of strength class C10 were tested, C14, were tested under reverse loading. 3 beams failed in tension, 1 in shear, and 1 in compression at the previous ones. The comparison of the characteristic values for strength classes C10 and C14 for GLT beams made of oil palm timber, here grayed out in the table, to the standardized characteristic values for softwood are in the table. As the comparison shows, the characteristic strength values of strength class C14 for softwood are achieved, except for GLT beams made of non-whipped lamellas of C10. Furthermore, the characteristic strength values of the whip-based beams are higher than the targeted strength classes. The characteristic stiffness value for coniferous timber are not achieved with GLT beams made of oil palm timber. The values for the average density and the characteristic density for oil palm beams meet the requirements of the standard. Finally, it remains to mention that the ratio between MOR and MOE for oil palm is significantly lower compared to the ratio for softwood. Now I come finally to the conclusion. By grading the boards according to the density distribution across the cross-section of the board, the bending properties can be optimized compared to the conventional method of lamella production. Furthermore, the beam design or the quality of the lamella and the beam structure has an influence on the failure pattern. The procedure for calculating a particular strength class is generally correct. Both classes achieved with whipped lamella-based beams. The existing characteristic values for the classification of softwood does not apply for GLT made of oil palm timber. So if anyone is interested in the used literature, please send me an email. And now I come to the last slide. Thank you very much for your attention. And also many thanks for the research funding and all partners for their support. If anyone have questions, please feel free to ask or post them in the chat. Thank you.
Thank you very much, Lena. So as Lena asked, if you have any questions, feel free to type in the chat, because at the moment we have no questions. there's no question, I would ask you, Lena, if you compare glue laminated timber from oil palm wood with glue laminated timber from softwood, which we use in Europe, or I think all over the world, are there differences in the principle of the build-up? So if you look, for example, at the fracture patterns, what do we learn from the fracture patterns?
Yeah, mostly the fracture pattern was in the compression lamella, and normally, or it should be in the tension lamellas. So we have to overthink our beam setup. Yeah, because of the because of the quality of the lamellas and the
So you gave me some work for the grading, which I will present later on. So I think that's the point, that grading is one big topic, because the elastomechanical properties of the oil palm wood is different from common tree species, and therefore it behaves totally different if you have a loading, and therefore we have to work a lot on grading and the